terminology. I mean, any theory should start from basic terminology, a kind of, providing the language to discuss together. Like if you want to go abroad, if you want to study in the US, etc., you have to learn English. And the same thing, if you want to do something in your career as an engineer or maybe for your further study, you need to know the language of graph. Okay, beside the language of probability in lecture 7, now lecture 8 provide the graph theory, and we start from there. Basic definition. Okay, we call the terminology. Terminology means definition, if you want to say that. And after a few terminology, then we need to know some specific or special graphs. I list here in total 7 kind of graphs, but actually in the future you need more than that. Okay. This provides the fundamental block of making new graph and to solve practical problem. We have complete graph, we have cycle, we have NQ, we have didactic. I mean, the one number 5 and number 6 here very important for application. You will see. Then after that, we go back to the generic graph concept. We discussed a few ways to represent, to describe graph on computer. Okay, how can we tell computer understand about the graph you are studying? Huh? Then we also learn about the graph isomorphism. In terms of exercise, there are a lot of, but we can group them in a few categories like that. You see the bipartite appear again here. That means that structure is important. Okay. So in terms of outcome, the expectation the society and the university expect you to have after studying lecture number 8 will be the blue here. In overall, you have 4 major learning outcome or learning category you need to obtain, but look specific to LO1. Okay, L mean learning, O mean outcome. Then you see here the 1.2. Okay, you need to be able to define some, basic discrete concept and structures. Set and mapping, and today we learn graph. Okay. Secondly, in terms of the second outcome here, you should be able to represent and then describe and modeling practical problem. Now, specifically, you need to know how to employ the graph considered to be a special or discrete structure. Number 4, after you know the theory, then you should be able to manage to provide some operation on graph, namely how to compute some quantity inside the graph, how to optimize some quantity or some new measurement on the graph. Okay, so this is a very brief learning outcome you have to keep in your mind. Then the first question you should ask when you want to study something new at the beginning, that you should try to ask yourself, why do we need that learning? Okay, why should we study the structure? Okay, and the answer for graph theory is very easy, because in computing in particular, a software engineer, a project manager, is a hardware builder in computer, etc. You need to know how to represent the structure. shorten some structure and then optimize something. That can be seen in hardware, computing, like to build up new electric or electronic main board in computer. You need to, for instance, the second one, network. I mean, connect the computer on the internet so that they can understand each other. And now many new things in the AI and big data era. Okay, the application can be any section in military science, in traffic engineering, in environment, in medicine and social management, logistics, and airline industry, etc. So, briefly speaking, we can say that graph theory is useful for analyzing things that are connected to the other things. So if the things, I mean, in our life, they do not connect, then you don't need to learn graph theory. But the reality is that any things in our world connected together. You see, HCMUT located in Little Creek Street, and that street led to another sector of the city, and the street connect together. That kind of thing can be described by graph theory. In medicine, for instance, the second sector, we can say that you need to understand why people get sick by some reason, and the connection between your food you eat every day, the way you live, etc., then also impact on your life, and things connect together. In your brain, we talk about neuroscience. The same thing can happen. Okay. In traffic engineering, why so many vehicle accidents happen on the highway? Is there any way to represent that kind of phenomenon? Everything connected then requires graph theory. There are some easy problems, but there are some more difficult problems. But in any way, easy or difficult, graph theory is always useful, because without them you cannot have a model. Without having a model, you cannot use computer to solve the problem. And down to the earth, the graph theory is there. So we start from the first definition today, and for your career as well. We define the graph. Okay, we start by looking to a graph G, and briefly speaking, this is a pair, not one structure. This is a pair of structure. There are two entities here. The first one we denote by capital V. We call the set of vertices or the set of nodes. So there are two equivalent terms you can use. Either the element inside V we call vertex, or the element we call node. So we say V is a non-empty set of vertices or set of nodes. Okay. Then the second component in the graph G, the second one here, we denote by capital E here, namely the set of edges. We need to specify clearly what is the meaning of edge, but right now, just accept the two components here. They together make up the graph G. Okay. So in general, in the most generic case, a graph captures the abstract relationship between the vertices. We don't know yet what kind of vertices or what kind of nodes we study, but we understand this structure abstractly. Okay, so let's see sample and to see how can we build up the graph from two components here: the V, the vertex, and the E, the edges. The vertices or the nodes are the orange circular here. I put the number inside to number them. Okay, so in this case, the graph G, we have 4 vertices: 1, 2, 3, and 4. So the orange node here stand for the notch or the vertex of the graph. Together, they make up the capital V. So number 4 is just one notch, but you have 3 other one, the number 3, number 2, and number 1 as well. So if you want to represent this one, you have to write capital V in terms of set function. Okay, you have to use the bracket out here, and you put the number 1, number 2 inside, and you have to bracket at the end. So this is V. Then we move on with the edges. So by default, this one, the one here, connection between 1 and 2, we call the first edge. Okay, so briefly speaking, we understand that the edge set consists on connection, possible connection among the vertices. Okay, so you can write the first one here by the notation E1 here, E1, to represent for the S from 1 to 2. Okay, there are 3 more E1 there, and this one is the second edge. I can denote by E2. Okay, so there are more. So also we have connection from the vertex number 2 to vertex number 3 as well. We can denote by the third edge. Okay, so we understand edge just kind of connection between a pair of vertices. So this structure we call undirected graph because you don't see the direction on the graph. But if you look to the second one here, by the same set of vertices 1, 2, 3, 4. But now when I define connection from vertex 1 to vertex 2, I allow the error here, error. Okay, so that means we tell the direction from 1 to 2. Like the one-way street in Ho Chi Minh City, you know, there are some two-way. So two-way we can write on the left-hand side here. The car and the motorbike can run both ways, from 1 to 2 and from 2 to 1. But in the second graph on the right-hand side here, you see that the motorbike and any kind of vehicles can move only from number 1 to number 2. So this one we still can denote by E1, but now you have to understand that you are talking about directed connection from 1 to 2. Okay, and if every connection on the second graph having direction, okay, 1 going to 4 only, not allowed to go back from 1 to 4, and etc., then you have the second structure. You have to put the adjective here to say that directed graph means the one where any connection must have direction. Okay, so definition number 1 actually consists of 2 kind of almost the same, but not fully the same. So because the directed graph is more complex, so we study later, right? Now we focus on the undirected graph only. Undirected means no direction on the edges. We have the second definition defined on any undirected graph. We call the symbol graph. Okay, so you see here you see some connection from of the highway system in Vietnam, like the first one going from Lạng Sơn to Hanoi. So this is the one you don't see the arrow, right? So that means two-way connection, right? So from Hanoi you can go to Da Nang. Again, we don't write the direction. So this is the undirected graph. And there are some cases you don't see the connection line between Lạng Sơn and Da Nang. You don't have that connection. That means you don't have that edge. But you have Hanoi, Da Nang, good. You have Da Nang, Ho Chi Minh City, etc. Then the entire graph here we call symbol. If two conditions here fulfill. The first one, if you choose any edge like this one E, then that one must connect to different nodes. Okay, we don't allow connection like this one is not allowed. From Hanoi, go somewhere and then go back to Hanoi. We don't allow that kind of connection in symbol trap. So this one is not allowed. So if you have some edge, then one side start from Hanoi, the other side must finish in somewhere, not in Hanoi. Okay, like in Ho Chi Minh City. Okay, so we say that different vertices connect different vertices. The first structure I draw here for you, we call this one a loop. We don't call an edge, we call a loop. Okay, we do not allow loop happening in symbol graph, not allowed. So this is the first condition. Secondly, no two edges connect the same pair. The second one saying that if you have traffic, a highway from Hanoi to Ho Chi Minh City already exists by looking to this one, okay, then you don't have the other one. Only one connection or zero. We don't allow two actually connect the same pair of vertices, right? So you are not allowed to have this connection inside symbol graph. So the second connection like this one from Hanoi to Ho Chi Minh City, and again this kind of thing does not allow. So briefly speaking, either between two nodes like this, no connection, okay, and if yes, then only one. So not allowed two edges, okay. For this reason, why in symbol trap, if the two vertices U and V connected together, then you write that H by this notation. Because no direction, so you can use the set notation to write for this one. So if I apply the last argument here to the H from Hanoi to Ho Chi Minh City, then I have to write the connection E using this notation. What is U? The first point of that one must be Hanoi. You see what I mean, right? Hanoi here. Then what is V? Because we allow, in this case, connection from Hanoi to Ho Chi Minh City, okay, to vertices U and V. So the V now, it turned out to be exactly Ho Chi Minh City. And then you have to draw the connection by the bracket, because you represent the H by a subset, a set U and V. So the symbol trap is very useful because then you can compute something on symbol trap. You do not allow multiple. The second condition say you do not allow more than one two edges. So Đà Nẵng, Ho Chi Minh City, okay, only one. You see, Ho Chi Minh City, Cà Mau, also only one. Or zero connection, like Đà Nẵng, Cà Mau, no connection. Not allowed two. 0 and 1 are okay. And then after the symbol, then you can extend to the multi graph. Multi, that means you allow not only one, but maybe two, like this one. Hanoi to Ho Chi Minh City, one here, up. And in the future, maybe the government have money, then they can build up the second one here, E2. The second highway, the first highway can be national way number 1, and the second highway may be realized in the next 10 years, we don't know. But if that is the case, then we see there are two connections between the two major cities in Vietnam. In that case, we have to call this graph to be multi-graph. So this is the definition. Graph that may have multiple edges connecting the same vertices, you see. And if we apply this to the picture here, the concept multiplicity M defined to be the number of edges between Hanoi and Ho Chi Minh City, and the multiplicity for this connection will be number 2. You see, maybe you see there are two highway connect. So we study multiplicate the symbol graph because that simplify things and allow you to get precise result. But in general, in the future, in reality, you also have to think about the multi-graph as well, if necessary. Okay. Um, we talk about the loop, and you ask, well, after the multi-graph, then you see here multi-connection, Hanoi, Saigon, 2. But then you also allow the loop. I told you before, the symbol graph does not allow the loop. Now we allow the loop inside. So how many loops are there in this picture, guys? Tell me. Answer me. How many loops are there?
3.
3. Excellent. Tell me what is the maximum multiplicity in this trap? There are 3 loops or 3. So this is one loop Hanoi, the second loop in Da Nang, and the third one Ho Chi Minh City. But I ask what is the maximum multiplicity? You just study in the previous slide. Who can tell me what is the maximum of M? Because this is the multi-graph, so we allow between two vertices there are more than 2 connections. And you see the picture here, we define the multiplicity M. You see the number of different SG connect. So you see here Hanoi, Da Nang, M. How much? Hằng, tell me. Hanoi, Da Nang. Thúy Hằng. Hoàng Lê say number 6. Wow, so 1, 2, 3, etc. No, not 36. No. I asked you how many. I mean, you have to count the multiplicity between any pair of vertices. Phạm Hữu Đức say number 2. That's excellent. Because if you count between Lạng Sơn, Hanoi, you see M to be number 2. You count between Hanoi, Da Nang, also 2. Hanoi, Ho Chi Minh City, 2. You see? Ho Chi Minh City, Cà Mau, 1. Okay? Then, no more. So, what is the maximum value M? Đức say number 2, correct? Phạm Hữu Đức. Đức gets 1 bonus point, okay? You have to count every multiplicity, then you choose the maximum value. In this case, the max of M turned out to be number 2. You see? No more, no less. I don't ask you how many. Multiple axes. No. I ask you what is the maximum multiplicity in the entire graph. So this one provide 2. This one provide 2. This one provide 2. Etc. And there are 3 groups. That's fine. So everything depends on the concept. You have to be very, focused on the mathematical concept. Don't forget that. And there are a lot of definition in one day from today. You have to be careful, okay? Now we extend the concept to the directed graph. Remember, we defined the directed before. The concept V, we don't change the set of vertices. But for the E, you allow the direction. So this one we call the set of directed edges. In some textbook, they can denote that one by the new name, the arcs. Okay? So between Lạng Sơn and Hanoi, how many arcs do we have? How many directed edges do we have, guys? Lạng Sơn, Hanoi, 2. Okay. And you have to be careful now. Lạng Sơn to Hanoi, you have to write E1, 1 arc. And by definition, Hanoi to Lạng Sơn, you have to use different notation. The other way around. So from Hanoi to Lạng Sơn, you have to write by using the second notation E2. They are not the same. Okay. So the same thing from Da Nang to Ho Chi Minh City. You see the arrow here. Da Nang to Ho Chi Minh City one way, and then you see the arrow here. Ho Chi Minh City back to Da Nang. So again, the one connection here are different. One way Da Nang, Sài Gòn, with the other way Sài Gòn, Da Nang. Okay, so you have to be careful when we talk about directed draft. Therefore, we can say, well, directed draft, they are different because they start differently. Okay, the E1 from Lạng Sơn to Hanoi, that means you here start at Lạng Sơn and finish the highway at V to be Hanoi. And then you see I am not allowed to write notation subset like before. In the undirected draft, I can denote an H like this one. But for the directed draft, this one is not precise. This one is fail in directed draft. In directed draft, to have the H with the direction, then you have to write this one. The bracket, I mean the pair of, with the ordering between the vertices. So everything must be very precise in the draft theory. Okay. Then there are more because things more complex. So I again go back to the simple case. We consider undirected again. Okay, no direction. Then if the HU defined in this undirected draft by two vertices U and V, like this one, understand? Right? Then we say that the U and the V are called adjacent. Okay, they are neighbor. They are neighbor because they can connect via this connection. We say that because they are the endpoints of this connection. Okay, adjacent. That means there are some root between the two nodes. So your home may be at the U and your girlfriend at the V. The two homes are different, but there is a root connecting the two homes. And we can say your home and your girlfriend, home are adjacent. The two homes, the two houses, we call the endpoint. Then you can say the root connecting the two houses is incident with both the first node and the second node. Incident with, okay. We can also say the HE to connect the first node and the second node. So there are two ways to talk about E. Okay, the connection E incident with node U and V, or the connection E to connect node U and V. So not only the notation but also the term, English term, you have to be very careful. Incident with or to connect, but the node themselves we call adjacent. Then after we define that one, we can move on to the important definition here. We define the degree of any vertex. So in the draft, let's say undirected draft, you are given a vertex, then we define the degree of that vertex, okay? And we denote it by this one and define to be the number of edges incident with that vertex. Except if you see a loop, okay, then you have to count twice to the degree of that vertex. Otherwise, you have to count only one. So you have you here, your house, okay, and you have V here, your girlfriend house, and you have a root connection from here to there. But also you imagine that if you have another knot are denoted by W, maybe your school, then there is a route connecting your house to the school. Let's say HCMUT here as well. So you have to count the number of H incident to U. And by the definition, you have E1 here and E2 here. The number of HC to be number 2. So the degree to be number 2. Understand? But if you see a loop like this one, I mean at your home there is a route go to some park, garden nearby. So if you follow the last figure here, I have to say that the degree of the vertex U must be number, which number, guys? Follow the picture here. Tell me the degree of the knot U. Number 4. Good, Bảo Ân. So the first guy will get. So let me choose the first guy who answered that. Khánh Nam. So the first guy answered. Khánh Nam got 1 point for that one. Khánh Nam get 1 bonus point. I mean, if it's easy question and a lot of guys, then I have to choose the first guy to give the precise answer. Okay. Then we go back to theory here. If the degree of some vertex, we count everywhere, but we see only 0 degree 0 for that vertex, we call that one isolated. And if the degree of the vertex to be number 1, we call pendant vertex. So more than 10 definitions so far, you see, a lot more, maybe 30 or something like that. This example I don't show. I just show you the graph, the left hand side and the right hand side here. They are all undirected, you see. And you have to apply the definition to count, to compute the degree. So if I say the right hand side 1 here, C become the pendant vertex because the degree to be number 1. The left hand side here, G we call isolated vertex because degree to be number 0, etc. So you can do this exercise yourself in 1 minute, no more, no less. In the second trap, more interesting because you allow not be here to have a loop. And if you count, you see the degree must be number 6. You see, number 6 by our concept. 1, 2, 3, 4, 5, 6. So you have to be careful here. The degree of B to be number 6. You see. So that's the same with the knot down here. So very easy exercise. We don't count that, but we have to employ this one in many problems later. So actually this one is the first theorem in graph theory, the most simple one. This we call the hand-checking theorem. We are given some graph, undirected graph, and we assume that the graph have m edges. So just undirected graph any, and you count m edges. Then you have this equality connection. The left hand side 2 times of m, and the right hand side will be the summation of all degree, where you allow the vertex move everywhere in the vertex set. Okay, summation over entire vertex of V capital. Okay, this is the degree. So we apply this one for not only for the symbol but also for the multi-graph. Okay, multi-graph allow with the loop as well. So it's very general. Okay, 2 times of m equal to the summation of the degree. You have to keep in your mind in that way. Then after theorem 1, we can say this one is the second theorem. You claim that for any undirected graph, you observe the vertices with only odd degree. Odd means number 1, number 3, number 5, odd number only. And you count how many odd degree vertices are there, and you see that the number of them must be even number. So if in the graph you observe 3 vertices with the degree like this one, so this is never happen in the real life. In the real life, the number of odd degree vertices must be even. Even mean number 2, number 4, etc. Understand? So therefore, in any undirected graph, you don't have the last case. If you have odd degree, then you have, this is 1, this is the second, there are 2. 2 is even number. Okay? So after using the second theorem here, then we get the first outcome. We call O1. You can read and you can check yourself by apply to the previous example. Okay, I mean the graph we had before give you the outcomes here. I mean not only O1, but you have O2 as well. O2 as well. So before read the O1 and O2, let me check this one first in your graphs before. The number of odd degree vertices to be even number. So let's take a look back there. Count the odd degree vertices and to see is that true or not. Look to the graph G on the left. Okay. Can you write down the vertices having odd degree in the chat box? Write the vertices having the odd degree in the graph G on the left here. Who are they? What are they? Which one? How many? Which one have odd degree? Which one? For the graph on the left. You have one more 10 seconds. Otherwise, after that, I will write the answer. No one answer. Okay, so this is my answer. Only two not. Oh, a lot of guys answered there 1 minute ago. So let me count from up down. So 940 up there. Khánh Nam give E and D. Correct, because he have degree 3 and D degree 1 and there are 2. That means even number. Good. So Khánh Nam get that, the first guy. So Khánh Nam get another point. So Khánh Nam today he got 2. Remind me, okay? Then you see the theorems, the second theorem is correct, you see? Apply to that case. Now we observe the outcomes. The number of vertices in that graph is odd number. If the number of vertices is odd number, then you have to observe one even degree vertex. So degree number 2, number 4, number 6, etc. Okay. So for the outcome, you have to prove yourself. I ask you to write a proof formally for the outcome O1 O2 and maybe O3. So this one is not O2, sorry. The last one here you have to write to be O3, not O2, sorry. So there are 3 results you can employ, and I ask you to prove yourself, okay? To write a mathematical argument to prove. So easy, everything rely on theorem 1 and theorem 2 here. I don't prove here, okay? So read the last one. For instance, if the number of vertices in some undirected graph is an even number, then the number of vertices with even degree also is even. So a lot of things here, but basically rely on theorem 1 and theorem 2, okay? In exercise, you apply. For the first practical problem in real life, we consider a traditional problem in your high school, perhaps you know before. So there are three entities, okay? A goat, a cabbage, and a wolf. They are on the same side of a river. So this is a river, a flow of water move like this direction, something like that, and the left hand side of the river on the bank of the river A. So there are three entity: a goat, a cabbage, and a wolf, okay? And then also a man, a boatman. So there are 4 entity, and the boatman wish to transport them to the other side, but the boat is too small. Then he could transport only one of them at once. So if he choose to go with the goat, then the cabbage and the wolf must be stay on the river bank A on the left side, not moving. And after he moved the one here to the second side of the one, then he go back and continue to bring the second entities, something like that. So the question is, how can he proceed not to lead them together without surveillance? Very important. If the first time he go with the cabbage, this is not good because the wolf can eat the goat. Wolf eat the goat. So if he go with the wolf, then the goat will eat the cabbage, you see. So there are some certain rules you have to meet to not destroy the entity on the left side of the river. So the boatman have to move them to the other side, but he have to keep in his mind the rule. So how can we solve this kind of problem? Only one way, by using the graph theory. And you have to read this one at home, okay? So B here mean the beginning, the boatman. This is the goat, the cabbage, this is the wolf. And we write here, that means nothing change, okay? Then the first move will be like this. The boatman go to the other side of the bank with the goat. He left the cabbage and the wolf because the wolf does not eat the cabbage, you see. So this is a legal move, good move, okay? Allowable to change. Then after he brought the goat to the side, so this is the left hand side A, and this is the other side of the river denoted by B, you see. Then he go back, he go back So you have to read the draft here to understand what happening. Okay. He go back and then he continue the story by choosing another choice, right? So we continue the second move by observe here, because after he let the goat get out from the coach, then this one alone there, he go back and continue moving, okay, continue moving the other entity. So you can see more formal solution in the tutorial, or actually in the extra reading where I model that problem. Okay, I provide the full solution in the extra reading for modeling the draft. I give you there. So I provide the information in the email. You got email here, right? And this is the hint for that. Download the extra reading for modeling by draft, and you see the basic techniques for solving this problem. I don't solve it now because we have to learn the theory. Okay. So you have some situation, you have some requirement, and you need to find a solution, and that solution requires draft theory. Now we go back to our theory. So this is just the warming up. There are a lot of exercise to practice this one. For each exercise here, you try to solve the best within 5 minutes. Not long. Okay. So for instance, in the first exercise, you read here: is there any undirected and simple graph having 4 vertices? And also we know the degree of the vertices like this one. Is there any graph like that? You have to write a solution to answer yes or no. Okay, by employing the first 2 theorems, the Hansen theorem and the second one I just mentioned before. The second exercise may be a little tricky. You see, maybe longer, bigger size problem, but the same kind of things. Exercise 4, exercise 3. So the larger index means the more difficult. Okay, and if you can solve this one within 40 minutes with the full solution in precise and beautiful English sentences, then you are successful. Okay, so for instance, the last one here, I provide you undirected and simple draft. You know the number of edges, you know some vertices with the degree, and some other vertices with different degree. Then we need to add the number of vertices. So have to employ the theorems. If we have time, we go back to this exercise to solve later. Okay, but right now we move on. The draft modeling can be used more efficiently in communication like this one. Okay, so this is a real life problem, and this is considered to be the first decent problem for this part. Read this one and try. Okay, so before we finish the first hour today, let me finish this slide. We move to the second objective today, discussing about how can we represent a draft inside computer. So there are 3 ways. First of all, we consider the first way, represent the draft by a matrix, actually a binary matrix. Okay, so this is the assumption. You have undirected draft denoted by G with the two components V and E. Will say something here. The second is no. Very fast. Let me check Phương Nguyên answer. Phương Nguyên answer. Nguyên, tell me. You say no for which exercise? Phương Nguyên. 1, 2, 3 or 4? Which one? Number 2. We said that we asked, is there any symbol graph with 6 vertices and the degree is like this one, and we count 1, 2, 3, 4, 5. That means when we take the summation of the degree, you get in total the summation will be 17. This is the summation, and by the Hansekin theorem, the other side of the equality must be 2m, and m must be natural number. Then if we follow the assumption here, m is not natural number, so that means there is no trap. So the answer by Phương Nguyên is correct. No graph exists in exercise number 2. So we got 1 bonus point for this. Okay, thank you, Nguyên. Lê Hoàng answer at the same time with Hòa, etc. Let me see. Đức, the first guy, 9:56 a.m. Đức say yes. Đức, tell me, you talk about exercise number 1, correct? Phạm Hữu Đức, you say yes, exercise 1. So we can check that one. He said yes. We confirm there is a graph. So by using the Hansekin lemma or theorem, so 2m by the summation of the degree, and the summation turned out to be number 6. So we have m to be number 3. But Đức, can you draw the graph? Because sometimes the solution we get from equality, but you cannot draw. So in that case, can we draw the graph like that? 1, 1, 1, 2, 2, with 3 vertices. You draw yourself the graph, and can you show to the class from your screen? Đức, Phạm Hữu Đức, I will turn on your video. I pin you to screen. Can you draw the graph for that, Đức? Tell me in audio. Yes or no? No. Đức say no. Although we get m to be number 3, so actually he cannot draw the graph. So that means you have to say the answer of exercise number 1 must be no, because that reason. So be careful. Sometimes we get the value m and the number of vertices, but you cannot draw the graph. So the conclusion will be no, not yes. If you can draw, then you get the bonus. Otherwise, we move on. Let's check the other guys. Okay, the whole class check his answer. So we finished now faster about the representation by matrix. So you assume the vertices like this, Vn up to Vn. So this is the V, Vi, and the matrix will have the sign n by n. And if you locate the row I and column j, if the vertices connect to build up a H, then you have to write number 1. Confirm the connection. Otherwise, you have to write number 0. Okay. No exists the H, then number 0. Therefore, the graph here become a Boolean matrix. Boolean means allow 0 and 1. That one we call adjacency matrix. So very simple like this one. Okay. If yes, number 1. If no, number 0. Adjacency matrix. So this one is the first example, and you see A and B connect. Yes. So you see at the entity like this to be number 1. You see. And let's see B and D, no connection, B and D. So if you observe the row B and the column D, the entry line, that one will be 0, you see. Similarly for the C and D, also 0 because no connection. So if yes, then you say number 1, like A and C, yes, you see. So this one we call adjacency matrix. This is the adjacency matrix, okay, of the matrix G. So I give this example to let you understand. But in the second example, you try yourself. I don't solve, okay? I give the other way around. I give the adjacency matrix first. It's we move on, not some exercise. We can do yourself, okay? We are move on with the theory, otherwise we cannot stop in time. In the second example here, I give you the adjacency matrix. I ask you to draw the graph G itself by providing the vertex and also drawing the edge inside the graph as well. So this one finished the first hour today, and we take a break, and then we resume after. So we resume here. Okay. 9 minutes. Okay. Go back at 10:15. 9 minute break.